Okay, pause and copy this. Don't forget the table of values over here. Pause and copy. Okay, so we're trying to get an idea of what this might be, this funny looking integral here. What happened there? The strange thing here is that the interval is infinite. It's going from 1, which I forgot to write down here. It's going from 1 all the way to infinity. So, if you were to continue over here, this function would just get closer and closer and closer. Same with the blue guy. And the kind of area we're trying to find is this area here, which appears, at least in some sense, to be going on forever. So trying to find that area with this integral up here. So how are we going to go about that? Well, we will do what we did in Cal 1. When confronted with infinity, we're going to be very careful with it and use a limit instead. So we're going to say this is equal to limit of something. So what will we do? Well, the idea is to look at this area again and cut it off at, say, t. Put a t there. So just break it off there. Now the idea will be to find this smaller area here. And then afterwards, allow t to go to infinity. Okay, so we'll do the integral from 1 to t now of 1 over x squared. Thus finding this smaller area. And then we'll allow t to move to the right. Okay, that will be our approach. I hope you find that reasonable. So how we evaluate this is we forget about the limit for now and just leave it out front. Do the antiderivative minus 1 over x from 1 to t. And do limit. So we get minus 1 over t minus 1 over 1. We get limit minus 1 over t plus 1. Now t is going to infinity. So this dude here is going to 0. So we just get 1. So what are we saying? We're saying that this, let's erase all this nonsense. We're saying that this area that goes on forever and ever and ever, and with a curvature on top, when I calculate it in what I think is a reasonable manner, I get 1. Okay, let's try the integral of 1 to infinity of just 1 over x dx. So this one we will divide here. Use the same approach. We'll go limit t goes to infinity of the integral from 1 to t, 1 over x dx, which is lim. Now we have ln x from 1 to t. Don't need the absolute value because these numbers here are positive. So what do I get? I get limit ln t minus ln of 1, which is 0. So t is going to infinity. So what is ln? I'm not going to write this explicitly. This is just a thought bubble. Ln of infinity is just infinity. So this area ends up being infinite. Okay, pause and copy. Pause and copy. Let's scroll back up and see what's happened. So, what has happened? So I got the black curve is 1 over x squared. The blue curve is 1 over x. And the blue curve, you see how it falls slower, right? So this black area underneath is just 1. But if I look at this blue area, it turns out to be infinite. Okay, well, the picture doesn't quite show you everything that's happening. It's just, I guess the idea to simplify is that, you know, this curve here is just not coming down fast enough. So, use some special language here. We use a limit here, right? So, as we know, limits converge or diverge. So, we're going to use that language here. Convergent for when you actually get a number. And then for the infinity here, this is divergent. So divergent is when you do not get a number. You either get infinity or minus infinity, or perhaps just you can't resolve a number. Okay, so here's our definition, which we will take. So pause and copy. Pause and copy. Now, these guys here are called improper integrals, because there's something improper about the the interval that's being considered. So the idea is when confronted with this, we will replace it with this limit. Okay, don't forget this stipulation about continuity. So again, I want to repeat, convergent means convergent, maybe it's worth writing this down in a nice color here. Okay, convergent means I get a number. Okay, I work out this limit, and some number comes out. Divergent is any other outcome. Okay, it often means infinity or minus infinity, but not necessarily. There are other situations. Okay, example. Okay, so what do I do here? Well, this is just a integration by parts. But you start by going I guess in my definition I use A's and B's, but to be honest, I prefer using a T. I don't know why, it just feels a bit better. So I'm going to do integration by parts after introducing my limit. Okay, I want to emphasize something. Your first step must be to introduce a limit. If you do not introduce a limit, you will lose half the marks. So it's worth repeating. Use a limit in these questions, or you will lose at least half the marks. Okay. So what do I do here? I do integration by parts, which I believe is going to give me this. So I'm not going to show you my work, but we'll just say that. And then what? Then I can use my endpoints here. 0 minus 1 minus t e to the t minus e to the t, which is what? Clean this up. What do we get? E to the t minus t e to the t. And then minus 1 on the end. Okay, let's be careful here and separate this into 3 pieces. Okay, the limit of 1 is just 1. The limit, now t is going to minus infinity. Oops. Okay, so e to the t is going to 0. This one is actually tricky. Because it's, of the form minus infinity times 0. And that is, in fact, an indeterminate form. This part is pulling my overall expression to minus infinity. And this part is pulling my overall expression to 0. Okay, they're working against each other, And I don't know who wins, so I'm going to have to use L'Hopital's rule in this case. So I'm going to take it aside, think about it carefully. Now, to use L'Hopital's rule, I need a fraction, right? Okay, so I'm going to do a weird thing. I'm going to force this to be a fraction by pulling the e down. Okay, now I have something more familiar. Okay, the numerator is going to minus infinity, and the denominator is going to plus infinity. So this is a clear L'Hopital's rule situation. 1 over negative e to the minus t. Now I have 1 over infinity, which I can see is just 0. So overall, I get just minus 1. Okay, pause and copy. Exercise will be 1 to infinity 2x over x squared plus 1. Okay, you'll have to do substitution. So I'm going to stop this video now, but you should try that before you open the next video.